Have you ever wondered if you can mathematically represent Gauge infinity? Well, that's exactly what we're going to do today in lesson 1.2 of Calc BC, limits and limit notation. But before we get to Gojo, first let's talk about limits and limit notation. So, what are limits? Limits basically help us describe what happens to a function or a y value as x approaches a number or infinity or negative infinity. So, first let's actually write out limit notation. So there's three main types of limit notation we're going to be talking about. So the first one is the two-sided limit. So it's written like this. The first component is the lim, or the limit, and we just use lim to represent limit. And then under that, we're going to write x approaches a number. But I just wrote a just to make a general case. And then right next to this, we're going to write the function. So it could actually be like a function like x squared, or we could just write f of x, and then we define f of x somewhere else, but just for this case, I'm not going to do that. And then we'd say that equals whatever the limit equals as x approaches a. Then we have a left-handed limit and a right-handed limit. So how you notate these is really similar to the two-handed limit, except one key difference for both of them. So you start out the same way as x approaches a of f of x equals whatever. You would actually just add a negative sign to the top right of the a, or whatever the number would be as x approaches. And then for right-handed notation, you'd have the same thing, except you'd have a plus sign at the top right instead of a minus, and that indicates a right-handed limit. So how do we actually do limits? So let's take a look at a graph. So let's say we just have this graph of a line with the hole right there. Okay, so let's say this is A, and then this is 1, this is 2. Okay, so right here, how do we define the left-hand limit? So basically, what we do is we look at what the graph is doing as x approaches a from the left side. So that means when x is increasing towards a. So when x is increasing towards a, y is increasing towards about 1. So let's say that the left-hand limit equals 1. And then let's say the right-hand limit. So right-hand limit is when x approaches a from the right side. So that means when x approaches a from this way, the y goes downward until it gets to about 1. So the right-handed limit is 1. And the two-sided limit is only defined when both of these left-hand, right-hand limits exist, and if they're the same value. And when they are the same value, that means the two-sided limit actually equals the same number. So the two-sided limit equals 1. Now, what if instead of a being here, it was where the hole was, so at a? So now, if we do the same thing, we're going to go from x approaches a from the left side, we get y is about 2. So now that's our left-hand limit. And then we do the same thing from the right side. We get y is about 2 again. And since they're both the same number, that means the two-sided limit is also 2. And this is a key difference of why this does not equal f of a. And that's because f of a right now would be undefined because there's a hole there. However, the limit as x approaches a of f of x is actually equal to 2, a number. So that's what key difference is. And you have to remember that because that's a really important detail. Now we're going to look at a second graph. So let's have one graph here, and then a closed circle, and then open circle here, and then a line. Let's say this is 4, and this is 3, and this is, let's say 2. So now let's evaluate each of these limits at x equals 2. So as x approaches 2 from the left side, x approaches 2, and x approaches 2 from the right side. Okay, so first let's evaluate the left-hand limit. So as x approaches 2 from the left side, we get the limit as 3 because it approaches that from the left side. And as it approaches from the right side, it actually comes from here and it goes to 4. So that means the left-hand limit is 3 and the right-hand limit is 4. And since these are not the same number, that means the double-sided limit does not exist. So we write D, N, and E. That's how you represent that. And this is actually a good way of picturing how the left-hand and right-hand limit works, because when we approach it from the left side, we have basically a left graph and a right graph. So the left graph corresponds to this, and the right graph corresponds to this, and since these don't meet up at the same, they don't approach the same point, that means that the two-sided limit doesn't exist. Now let's come back to Gojo. So let's make a graph representing how far away we are from him when his infinity ability is active. So every time you get closer, you're about half a step closer, or half a measurement closer. So our graph should look something like this. Right, continues on, and it basically has a horizontal asymptote at 0, which is directly touching Gojo. So the way we represent this is using a limit. So we'd say that the limit, and let's call this function f of x again. So the limit as x approaches infinity, which is also the name of the ability, as x approaches infinity, because that's the horizontal asymptote, that of f of x is equal to 0, because the horizontal asymptote is the same thing as what the graph approaches as it goes to infinity, so the limit. So if we were to represent Gojo's infinity, this is how we'd do it. And we'd say the limit as x approaches infinity of f of x is equal to 0. Thank you for watching.